Okay, so that's March 15, 2022, and we will continue with the topic of capacitors and dielectrics. Don't forget that the exam is gonna be next Tuesday, right in here. Let me emphasize here. Chapters 23 through 25. Okay, so yeah, from 7 to 12. I'll try to put 7 to 12. Okay, and then you pick up a 2-hour time frame there. So 7 to midnight, you know, if you can handle that, stay until midnight. Here you go. Find the capacitance of two cylindrical concentric capacitors of radii A and B. So the idea is find out you have to find the electric potential difference between the surface A of the inner cylinder and the outer cylinder. Let me open the no, not this one. Where is my updated past PP student? No, not this one. Okay, looks like I have to get a PowerPoint here. Oh, yeah. Okay, right in here. PowerPoint. Good. And now that's what it is. Here you go. Okay. Cylindrical capacitor. Okay, here you go. Spherical capacitor. We do the spherical capacitor, and that's the cylindrical capacitor. Radius A, the inner one is radius A, the outer one is radius B. And that's what the experiment we did in the classroom. Okay, so here you go. We in the second experiment, okay, which was just like a configuration like this one. Okay, so we have to know what is the potential here at this surface and the potential here at this surface, and take the electric potential difference. It will always be, every time that we have something like that, you know, the electric potential difference will always be like a Q, magnitude of the Q, of the charge, right, times a constant that's given by the geometrical parameters of the capacitor, the radius, you know, and some C, you know, C is a constant that is, C is a constant that depends on the geometrical parameters of the capacitor. Okay, and let's see how we do the electric potential difference. You know, we did that before, right? So let's go. We got the electric field of the capacitor of the cylindrical of a cylindrical charge distribution, which is something like that. Okay, sigma A epsilon naught R. It decays with the distance, and okay, that's the electric field. And then you have to take the electric potential difference between point A and point B. when you do that, this inverse relation of R becomes a log. Okay, so let's do the math. Okay, we found, right? We found previously. I'm gonna even copy that. No, I'm not gonna copy it. Okay, we found previously. We found previously that the electric field of a cylindrical charge, cylindrical, don't forget, uniform charge distribution is something like that. Here you go. Is inversely proportional to the distance r, and that is a constant there. We can get that just by using the Gaussian law, by using Gauss's law. What else do we have? Sigma A epsilon naught r. Sigma A epsilon naught epsilon 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 naught r, like that. Okay, here you go. So that's the electric field, and that's the, here you go. Here's the Gaussian surface. Okay, and that's gonna be the electric field between this surface and the other one. Inside, the electric field is 0. Outside, the electric field is also 0, because the net charge inside the Gaussian surface is going to be 0. Okay? So now let's go ahead and apply the definition of electric potential. I'm going to get that VA more like, here you go. The right way to do it is not VA minus VB. The right way to write down is VB minus VA, and then you put the magnitude here. Capacitance is always positive. Okay, capacitance is always positive. Here you go, VA minus VB is going to be given, again, gotta remember the definition of electric potential. Okay, so here you go. Is from one point to another, is minus the electric field dot dr. Let me see if I remember. Vector. Vector? No. Arrow? No. Okay. Let's put this way. Well, I'm not going to do the vector. Okay, so going from point A to point B. Okay, from the initial to the final. And the electric field is radial. Okay. When we do the dot product, what left is just, it's not radius, right? This is the polar coordinate, and we can, I don't need that. This guy is getting in your way. So here we go. We can substitute this electric field right in here. What is constant? should be moved outside. The inverse of the r remains. Here we go. And we take the integral of r and apply log ln and apply the limits. From A to B. Okay. A to B. Okay, and we go ahead, apply the limits right in here. B divided by A. B and A are positive, so we do not have to worry about the log of a negative quantity. And we get this result here, which is negative. So we never get a potential difference that's negative for capacitors, right? So what we have to do, we have to take the magnitude here of this. Go. And that's what we get. Let's substitute now in the definition. In this definition here. And let's find out what the constant is going to be. Right, so here we go. Right in here. The charge is right in here in the sigma. Okay, so the sigma should be Q divided by area. Area of the capacitor. Area of the is gonna be 2 pi A times the length of the capacitor of the cylinder. Q. Okay, that would be the area. If I'm going to do step by step, let's do it step by step. Here you go. Should be this one right in here. Sigma Q divided by A, and A is 2 pi A times the length of the capacitor. Okay, I didn't give you the length of the capacitor because the capacitor is infinitely long. The cylinder is infinitely long, but don't forget that is also this Q is going to be magnitude. But doesn't matter, right? Because the inner one is positive anyway. So here you go. I'm gonna cancel this one right now. The A cancels out as well. And what's left below goes upstairs. Like that. Okay, so our constant is going to be this constant that you see right in here. It's going to be log of b over a 2 pi l epsilon naught. Okay, So the idea here, find not the capacitance, but find the capacitance per unit length, of two cylindrical concentric plates, concentric charge of radii A and B. So let's say B greater than A. So that's what we get. Capacitance and let's take a look at the 2 pi L epsilon naught log of B over A. 2 pi L epsilon naught log of B over A. Okay? And since we want, remember, we cannot get the capacitance of a cylindrical capacitor that's infinitely long. The only thing that we can get is the capacitance per unit of length of the cylinder, of this capacitor. Okay? But anyway, what you see right here is a very good approximation for finite length cylindrical capacitors. Okay? What you see above is the capacitance for an infinitely long cylindrical charge distribution. Okay? For this reason, we usually write the capacitance per unit of length. Okay? Either way, comma, the previous formula is still a good approximation for a finite capacitor, a capacitor of finite length. Okay? Even though either way the previous formula is still good. So if you have this capacitor that you built, just like one of the ones that I showed to you last time, right? What do? You measure the length of the cylinder. If you know the B and A, you plug it in there and plug the length of the cylinder right there, and you'll be able to find the capacitance of the device. So that's the another example of how you can calculate solve those problems. Here you go. Here is identify the capacity of two cylindrical concentric charges, two cylindrical of two cylindrical concentric charges. I should put uniformly somewhere here. Cylindrical concentric charges that are uniformly distributed. Okay, that are uniformly distributed. Okay, every example that we did here is for uniform distribution of charges. Find the capacitance of two spherical concentric charge distributions. Charge that are uniformly distributed of radii. That's okay. So here we go. What else can we do? Can we play? What else can we do? Okay, that's potential differentials. Okay, we did that, right? And those are examples, numerical examples that you can play with. Okay, example, another example, square plate, you know, concentric spherical, concentric conducting spheres of radius r and just numerical examples. What we want to do now is now we want to study what happens when we connect two or more capacitors, okay? They can be connected either in series or in parallel. They can be connected either in series or in parallel, just like we connected our resistors in the lab, remember? Okay? So the symbol for the capacitor is this one here. You already saw that. So we're using the representation of the parallel plate capacitor as the symbol. We can connect them in series or in parallel. Okay, here you go. Here's the capacitors connected in series. Two capacitors connected in series. One capacitor has capacitance C1, the other one capacitor has capacitance C2. And go. Okay, so here we go. And how do we connect capacitors? Just the same way we would do in a circuit with resistance. We connect them to a battery. We connect them to a battery. And how does it go? Okay, when we connect them to a battery, what's going to happen? The positive side of the battery is going to feed positive charges to one plate of the capacitor. Can you picture that? And the negative plate of the battery is going to feed negative charges to this other plate of the capacitor. But then something else happens. Remember that those capacitors and those wires are conductors, are made of metals. Because they are made of metals, the electric charge can move freely. So those positive charges are going to attract negative charges towards it and will repel the positive charges that were here. Those charges that are repelled move towards the other capacitor with the added help of this other negative plate that attracts the positive charge, right? Can you picture that? Simple enough? Okay? So here you go. Let's let's start. Let us start with two capacitors C1 and C2 connected in series. Okay? In order for them to work and become a functional device, okay, we must connect them to a battery. Okay? To work and become a functional device, we must, here go, one, step by step. One, connect them to a battery. Two, after connecting to a battery, the positive side of the battery will feed positive charges to the plate of the capacitor that is closer to it. Okay? Like what, right? Here you go. So if I were to play a movie, right? If I were to play a movie, it would be like that. Okay. Well, let me see. I'm gonna do it even better. We start with two capacitors that are discharged. That's a better representation here. It's not connected to the battery yet, right? So we are not going to. That's how we start. Let me see if I can take. I'm gonna take advantage of this picture here, so I don't have to redraw everything from the start. Okay. So here you go. We start with capacitors that have no charge whatsoever, and no battery connected to them either. Let's make it simpler, right? Because they are uncharged, initially there is no potential difference. No electric potential difference and no charges either. Just like here. Okay. In the next slide, here you go. Paste, right? In the next slide, we connect, here you go, the left plate of the capacitor to the negative side, to the positive side of the battery. I didn't connect it to the. Oh, wait a minute. In the next slide, let's do even. We bring a battery close to the capacitor. Let's put it this way. I didn't connect them yet. That's how we do in the laboratory. All right. Okay. It's straightforward. Can you see that? Let me show you a drawing of a capacitor again. That you are drawing a picture of a capacitor again, so you can picture how we can connect those capacitor right here in real life. All right, here you go. Capacitors are a device that has only two wires sticking out from them. Okay, there are some devices out there. Oh, here you go. Here you go. See two wires sticking out from the capacitor. Here's the cylindrical capacitor, two wires. Use two wires as well, right? If you're going to connect a capacitor in series with another, you're going to touch one of those wires to another wire of the other capacitor. I'm assuming that the capacitor doesn't have any polarities whatsoever. That's how you do in real life, okay? And then we go ahead and bring a battery. I didn't connect the battery yet. We first connect. The battery always has a charge in there. The capacitor don't have a charge necessarily. Okay, you go. When I connect the positive side of the battery to the capacitor on the left, okay, positive charges are transferred to the side of the plate. In the next slide, what's going to happen? These positive charges are going to induce negative charges on the other plate of the same capacitor. Okay, you go like that. But not only something like that's going to happen, but something else is going to happen too, right? Because we're inducing charges. Okay, I'm running out of. Careful. Okay, because we're inducing charges on this plate. Here you go, positive, negative, and there will be some charge induction in this plate as well. Okay, because of the left capacitor, yeah, there will be. There will be. It's not gonna be as strong. Okay, but yeah, there will be some. I'm not gonna say what is the. I would say it would be, instead of two charges, would be like only one. Okay. In the next slide, there will be again induction of charges in the other one. And then we connect the right capacitor to the negative of the battery. When we connect, then this charge here on the left side stays more. We have more charge here. Then it would be better if we put it like that, positive, like that. You go. That now that the both capacitors are connected to the battery, now we should expect that we're going to have a stronger, a higher concentration of charges there. Here you go. Here you go. Like that. Now there is something else too. There's something else that you have to know that happens. Okay, so I'm gonna put here Q1 for now. For now, okay. There's gonna be Q1 here for now. There you go. And I'm gonna put Q2 here right now. Q2 here for now. I put and because we have a charge, positive and negative charges in either plate, we are going to develop an electric potential difference between those two plates, and I'm calling that V1. Okay? Similarly here, because we have a charge distribution here, so it would be better, we are going to have a electric potential difference. And let's put it this way, since we're playing the movie, right? Here you go. That would be the better way to tell this story. Here you go. Now that we have an electric charge here on those two capacitors, there will be an electric potential difference built up between those two plates. And that's what we have in the next figure, okay? I'm gonna put Q1 here because Q1 was the first one. And I'm gonna put V1 here. Similarly, okay, C2, C2, okay, like that. What you have to know is the following. The charges on Q1 and Q2 are going to be exactly the same. That's what you have to know. For capacitors connected in series. Okay? They are going to end up with the amount of charge that we have here is going to be exactly the same charge that we have here. And one more thing, because this is energy, remember electric potential is related to energy, the battery is providing some energy to the capacitor, and energy must be conserved in this system. Okay? So the energy of this capacitor 1 plus the energy of this capacitor 2 must be equal to the energy provided by the battery. Make sense? That's how you have to think. So here you go. I'm going to spell it out that for you. Okay? After connecting it to a battery, the positive, let me see. After connecting the positive side of the battery, the positive side of the battery to one of the plates of the capacitor, positive charges will flow to that plate. Okay? And the plate will become charged. And the plate will become charged. Okay, similarly, after connecting the negative, here we go, after connecting the positive side of the battery to one of the plates of the first, let's see, called the first capacitor, right? After connecting the negative side of the battery, to one of the plates of the second capacitor, negative charges will flow to that plate, and the plate will become, you know, negatively charged. Okay, that's what we call the script of the movie, right? And it will become negatively charged, and it will become positively charged, okay? The positive charge of the first capacitor will induce the positive charge in the plate of the first capacitor will induce a negative charge in the other plate of the same capacitor. Okay, similarly, the negative charge on the plate, right? That should be negative charge on the plate, of the second capacitor will induce a positive charge on the other plate, of the same capacitor. Okay, both capacitors will be charged, and there will be a potential difference on them due to the charge distribution. Okay. Okay, and there's one more thing. When two capacitors are connected in series, so that's the little secret. That's not obvious, okay? There's a put like that. That is a little secret. There is a little secret that's not so obvious. That's not so obvious. Okay, when two capacitors connected in series are charged, they will end up with the same charge. And what does it mean? It means that Q1 equal to Q2 equal to Q. Okay? That's the little secret that's not so obvious. Uh-oh. Okay? On the top of that, now we have two capacitors with the same charge and different electric potentials V1 and V2. Here you go. V1 and V2. Okay. What else? Okay. Because, here you go. Anyway, it's gonna happen. I'm gonna put it this way. Because electric potential is a quantity related to energy, its unit is joules per unit of charge, okay? In order to have conservation of energy, comma, V1 plus V2 must be equal to V. Okay? V1 plus V2 must be equal to V. Okay? That's a statement of conservation of energy. Okay, so now we have, here you go. Now we have two capacitors with same charge Q and different electric potentials that, when summed up, is equal to the potential, to the electric potential of the battery. Okay, that's so. You have to have this idea in your mind to understand how capacitors work. Okay, I don't need that anymore. Let's see here. Yeah, I'm gonna delete this thing here. So I need another one. Okay. What's next? Okay. What we know is that those two capacitors, when connected in series, they behave just like a single capacitor with an equivalent capacitance. Just like we had two resistors connected in series behave as a single resistance with a equivalent resistance, we have the same thing with capacitors. Make sense? Okay? So two capacitors connected in series will behave like a single capacitor with a different capacitance. Okay? So what I want to do is to calculate this equivalent capacitance. Here you go. When two capacitors are connected in series, comma, they behave like a single capacitor with a different capacitance. What we want to do? We want to calculate different capacitance that we call equivalent capacitance. And we abbreviate by the symbol EQ for equivalent. Okay? What we want to do? We want to calculate, we want to find what is the relation between this equivalent capacitance and the other two capacitors, Okay, so that's what the problem that we're posing for ourselves. 5:45. Let's see if there is time for us to cover that. Okay, so here you go. Okay, so let's say that the equivalent capacitance is CEQ. We do not know that, but we do know V. Okay, we do know V. We do not know Q, but we do not need to know Q to find out what C equivalent is. Okay. So because we have here you go. Let's go back. Here you go. Let's just start the show again, right? The movie again. Here you go. Capacitors. Two capacitors in parallel. They're currently discharged, uncharged. We're going to start connecting them to a battery. We bring a battery close by that has a negative and positive charge distribution, electric potential difference V, energy. The battery is carrying energy. We are going to connect this battery to the first capacitor, and positive charges are going to migrate to that plate of the capacitor. These positive charges are going to induce negative charges in the capacitor. Okay, in that first capacitor. We don't need that yet. Okay. So these positive charges are going to attract negative charges to this plate. Okay. And then, similarly, these positive charges are going to repel some of the positive charges that are around here. Okay. And we're going to end up with also negative charge there. But when we connect the other end to the negative side of the battery, then we have a stronger charge distribution in both capacitors. We call that Q1 and Q2. Capacitance 1, charge 2. Okay? So because now we have a charge 1 and charge 2 in there, it means that we are going to have a potential difference. Every time that we separate charges, you create a potential difference between the separation of charges. So we get electric potential V1, electric potential V2. Okay? That's the final situation that we have when you connect them in series. Well, like I said, those two capacitors, they behave just the charges that, okay, first, the charges Q1 and Q2, when the capacitors are connected in series, they are equal to one another. Okay? And the electric potential V1 plus V2 should be equal to V because of conservation of energy. This capacitor with two capacitance here, these two capacitors connected in series, behaves like a single capacitance that we're going to call a capacitance with an equivalent capacitance, CEQ. The capacitor with a equivalent capacitance is going to have an electric potential V that's the same as this battery and the same charge Q that we had before. Okay? So now let's find out what's going to be, how can we write the equivalent capacitance of this equivalent capacitor. Okay, well, it's we do the following. We go back here to the, so we can medically we can state like that. We go back to our definition of capacitance. I'm going to simplify my notation. Here you go. I'm going to go back to the definition of capacitance. From now on, I'm assuming that the charges are positive and the electric potential difference is positive. Okay, here you go. Definition. Q divided by V. Okay, and this guy here is going to be my equivalent capacitance. Okay, let's not forget that Q divided by V is going to be V1 plus V2. Okay, what else do we have to do? Okay, we have to do something else. I'm going to do something else. I'm going to take, there's a little trick here now. There's a little mathematical trick. Finding, here you go, finding the equivalent capacitance. Okay? What I have here is just the definition of capacitance. Charge Q divided by V. I know what V is, V1 plus V2. The charge Q, okay, we're going to get there. We're going to get there. In reality, we do not know V1 and V2. All we know is that they sum up to result in C. Okay, that's what they sum up. So there is a little mathematical trick. We use a little mathematical trick. Here we go. Instead of getting C equivalent, instead we get the inverse of the C equivalent. Okay? And when we do that, you know, something interesting happens. It becomes easier okay, here you go. It becomes something like that. Q here. Here you go. I don't need that anymore, right? And then what can I do? I can dismember this, each of those terms. Okay, this term here, and this other term here. Oh no, not what I want to do. Here you go. Let's see if I can get it. No, not gonna do it. I'm gonna do like that. Here you go. This one. It's easier if you do in the paper, right? Sometimes it's easier if you do in the paper. Here you go. See, I'm dismembering here. Now, what do I do next? I recognize, okay? I recognize that C1 and C2, which is something that we know, we usually know from the manufacturer of the capacitor, we recognize that C1 and C2 is going to be given by what, according to the definition of capacitance, right? Q divided by V1. Remember that? And same thing for C2, right? Same thing for C2. Okay? If we substitute those two relations right in here, let's see what happens, right? What I have here, what I have here is the inverse of what I have here, right? Consequently, that first term can be here written as 1 divided by C1. 1 divided by C1. Here we go. And the second term can be rewritten as 1 divided by C2. And now we know how to calculate the equivalent capacitance when you connect two capacitors in parallel, in series. That is the equivalent capacitance of two capacitors when they are connected in series. Okay. If you have any capacitors connected in series, the equivalent capacitance is going to be given by will be given by yeah. It's possible to prove that. I'm not going to prove that because it's too much work. Okay, here you go, like that. One, two, three. Okay, which can be here written in a shorter summation. Let's see. No, summatory. No. Sum? No. Okay. So I gotta do it the long way. Okay, here you go. I from 1 to n, shorthand for what you saw there. And I can erase everything else. Can you remember that? Capacitors connected in series have an equivalent capacitance, which its inverse is equal to the sum of the inverses of each separate capacitors. Okay? So it's 5:55. Let me take attendance here. Nope, here. No, it's not what I want. Okay, that's an old version. Microsoft Office. Excel. Ten, let's see. Days. Last time was 10. Today is 15. Mario Acevedo. No? Toby? There. Let me pause my recording, okay? And okay, so here you go. Two different capacitors. One larger and the other one is smaller. So I can connect them in series like that. Because those capacitors have polarities, you gotta make sure you connect the positive side to the negative one of the other, okay? So negative is here, here you go. Negative, positive. This one is also negative and positive. So we connect them properly. Okay, so that's how two capacitors in series look like. The same way that two resistors in series look like. Okay? Now what we're going to do? Now we're going to find out what is the equivalent capacitance for two capacitors connected in what? Parallel. In the same way that we connected our resistors in parallel. Here you go. That's how we connect two capacitors in parallel. And we are going to go through the same step-by-step procedure that I did for two capacitors in series. Okay? So what I'm gonna do, I'm just gonna copy what I wrote down here. Here you go. I'm gonna paste, and I'm gonna make small changes because, okay, so now we start with two capacitors connected in parallel. In parallel. In order for them to work and become functional device, we must, one, connect them to a battery. That didn't change here. After connecting the, okay, so now it's going to be a little bit different because they're in parallel, right? So here you go. Two capacitors in parallel, right in here. I'm going to start with those capacitors uncharged because we didn't connect them to a battery yet. They become charged only after. Only after. Hey, wait a minute. Something wrong here. Hey, I'm doing, okay. I'm looking at the wrong one. Okay, connecting capacitors in parallel. C1 and C2, right? Here you go, capacitors in parallel, C1 and C2. Here you go. They are uncharged right now. And then we're going to connect a battery to them. Here you go. I'm gonna do it step by step here. This time I'm gonna do a little bit simpler, okay? I'm going to connect, here you go. Battery. Here you go, just like I did before. Okay. Battery is waiting to be connected. Okay, here you go. We connect to the first capacitor. So again, you got a picture. Positive charges are going to flow to this plate of the second capacitor. Positive charges are going to flow to this other plate of the other capacitor. You know, remember, those wires are conducting materials. That's why something like that happens, right? So here you go. And let me disconnect that. And then we're gonna do that again so you can understand nicely. Let me just copy and paste several ones here so I don't miss. Go. So when we connect the positive to the plates of the capacitor, the two capacitors becomes positively charged because they are directly connected to this positive plate of the battery. When we connect the negative plate, oh, the two plates become negatively charged. Okay? And now that they are connected, here you go. What happens? We are going to have, first we have an electric charge. It's better to put electric charge here first, okay? An electric charge build up. We're gonna have an electric charge build up. And it is the electric charge build up that leads to the, and I have to put one there. Yeah, I have to put one there. You know? Similarly, we're going to have a build up of electric charges on the other capacitor. Now that we have a build up of electric charges on the capacitor, a charge separation, we are going to have an electric potential as well. Initially, I'm going to put V1. Okay, you go. But then, there is something. Remember, for two capacitors in series, the charge was equal in both capacitors, and the electric potential was different, not necessarily the same. Well, when we have two capacitors connected in parallel, the opposite is true. The electric charges are different, but the electric potential is the same. Why is that? Because this battery is connected in parallel to those two capacitors. The amount of energy that you have here must be equal to the amount of energy distributed here, which must be equal to the amount of energy distributed here. See the difference between between capacitors connected in series and capacitors connected in parallel. Okay? So here you go. Those two capacitors connected in parallel result in an equivalent capacitance with a electric potential V and an equivalent charge as well, not necessarily equal to Q1 nor equal to Q2. Okay, now let's calculate what's going to be Q1, what would be, the equivalent capacitance. Let's calculate what would be the equivalent capacitance. Here we go. We do exactly what we did before. Here we go. But let's write down the script, right? Connect them to the battery. After connecting the positive side, let's see. Okay, positive side of the battery to the plates. It's not just one of the plates, but to the plates, because now they are connected in parallel, right? To the plates of the capacitor, positive charge will flow to these plates, right? And the plates will become positively charged. Okay, and then I can go ahead, copy and paste this one here. After connecting the negative side of the battery to the other two plates, to the other two remaining plates, right? Negative charges will flow to these plates, and the plates will become negatively charged. I'm just repeating what you saw in the drawing, right? I'm just writing what you saw in the drawing. Now we don't need this paragraph anymore. The positive charge of the plate. No, now that we don't have to worry about. We don't have to worry about. Both capacitors will be charged, and there will be a potential difference on them due to the charge distribution. Here there is, because, here you go, because the capacitors are connected in parallel, they will have the same electric potential V of the battery. Okay, so here you go. So instead of having Q1 equal to Q2 equal to Q, now it's going to be V1 equal to V2 equal to V. Okay, in a way is the complementary. What happens to the capacitors connected in series? Now, what happens to the electric charge? Okay, what happens to the electric charge? Here you go. Remember, we have Q1 here and we have Q2 here. Due to the principle of conservation of charges, the equivalent capacitance must have an equivalent charge that's going to be Q1 plus Q2. Let me see if I have it here. Here you go. Okay, here you go. The equivalent capacitance is going to be Q1 plus Q2. Okay? Make sense? So the equivalent capacitance will be able to hold more charges. Remember, I have Q1 here in this guy and Q2 here. If those two are going to become a single capacitor, you must have conservation of charges. Okay, Q1 must sum up to Q2. So that's the little secret. But remember, what did you get for the previous one? You get V1 plus V2, right? Now we have two capacitors with the same charge. Okay, it's the same voltage and different electric charges, Q1 and Q2. In the first case, you have conservation of energy. In the second case, capacitors in parallel, you have conservation of charge. Okay, because the electric charge must be conserved. Electric charge. Let's see, now we have a capacitor with the same voltage. Let's charge Q1 and Q2. Let's see, I need one more thing here. Those two capacitors will have an equivalent capacitance. Equivalent capacitance. Equivalent capacitance CEQ, and an electric potential V, an electric potential V, and a net charge Q. I'm going to put and a net charge Q. Okay, let's talk about what Q is going to be. I even, wrote it down as Q equivalent. Okay, because the electric charge is a quantity that must be conserved. Okay, then the equivalent charge must be equal to Q1 plus Q2. The equivalent charge, let's put this guy here. Then the equivalent charge Q1 plus Q2. Okay. Okay, they behave, okay. Already said those two capacitors have, yeah, they behave like a single capacitor. So finding the equivalent capacitance of the single capacitor, that's going to be Q equivalent equal to C equivalent equal to Q equivalent divided by V. Okay? Okay, Q equivalent is going to be given by Q1 plus Q2 divided by V. Okay. Now this formula, this derivation is going to be a little bit easier because we do not have to make any okay, I'm going to do like that. Here you go. Q1 over V plus Q2 over V. We don't need a mathematical trick in this case. All we have to do is to remember that C1 is Q1 divided by V1, right? I'm gonna, which by the way is Q1 divided by V, right? And C2 is Q2 divided by V2. Q is Q2 divided by V2, which is Q2 divided by V. We recognize this one as being C1 and this other one being C2. So what we get? C1 plus C2. Okay. If we have, you know, in that's the equivalent capacitor to capacitors when they are connected in parallel. If you have any capacitors connected in parallel, the equivalent capacitor will be given by, simple enough, here you go. Here you go. Can you remember that? Here you go. Like that. So, summarizing, capacitors in series, okay, and capacitors in series, and capacitors in series, and capacitors in series, and capacitors in parallel. And capacitors in parallel. And capacitors in parallel. I want you, you know, I want to remind you what the equations that we had for resistors in series and resistors in parallel. Do you remember? We didn't cover that yet, but if you paid attention, okay, to my lecture, you're going to see that there is this difference for the equations for resistors in series and resistors in parallel and capacitors in series. Okay, do you remember that? I wrote that down there. We can prove that too. Okay, and resistors in parallel, and if you did the experiment properly, you verified this relation. Only for 2 resistors, right? We cannot do that for n resistors. It's going to take forever to do the experiment. Oops. like that. Is that easy to memorize? You know, equivalent capacitance and equivalent resistance is, they do the exact opposite. Okay, capacitors in series, resistance in series. Capacitors in parallel, resistors in parallel. All right, capacitors in series and resistors in parallel is the inverse, is the sum of the inverse. Capacitors in parallel and resistors in series is just the regular sum. Okay, so that's what we have. Here you go. Yeah, okay. What time is that? 6:36. I think that we can, let's see, let's do a little example here. Let's see if we can do an example before we get in something different. Oh, here you go. I have a table here. Let me show you the table. Okay, very important table, right? Here you go. Summary. I like tables. It's very difficult to build a table, okay? But once you manage to build a table, you can memorize what's happening more easily. Capacitors in series. Hey, wait a minute. Charges are equal? Oh yeah, charges are equal. And charges are summed, right? When the capacitors are in series, the charges are the same. Q1 equal to Q2 equal to Q3 equal to Q, to Qn. Okay. But the equivalent capacitance of capacitors in parallel, the equivalent charge is going to be the sum of the charges. Okay. And then what happens to the voltage whenever you have capacitors in series? The voltage is summed up. Okay. For capacitor, so here you go, voltage summed up, charges summed up, right? Capacitors in series, voltage summed up. Capacitors in parallel, charges are summed up. See the little, cross that are making here? Okay, that's the relation that we get for capacitors in series and parallel. And then what happens to the final number? We can prove that mathematically. The equivalent capacitance for capacitors in series is going to be smaller than the smallest capacitance in the set. It's possible to prove that mathematically. It's possible to prove that mathematically. Okay? And the opposite here is going to be true. The equivalent capacitance is going to be larger than the largest capacitance in the set. Okay? It's possible to prove that mathematically. So capacitors in parallel have the same voltage across their plates. Capacitors in series have the same charge across their plates. And the next, let's see, we have would be nice to come up some examples here before we start working on this energy thing. Let me see if I have one here. We don't have it. Yeah, I'll have to. Yeah, let's go ahead and put some actual numbers there. Okay, so here you go. Okay, so here you go. Example. The simplest example that you're going to see about capacitors is two capacitors in parallel. So let's say C1 is equal, let me see here. I have two capacitors here. This capacitor here has a capacitance of 1 millifarad. 1,000 microfarad. Okay, so here you go. One millifarad. Here you go. And the other one. Let's see what's the capacitance of the other one. The other one here is a capacitance of 470.47 millifarads. 0.47 millifarad. Okay, find the equivalent capacitance. Can you do that easily? Right, capacitors in series, right? In series, no, in parallel. Here you go. This one here is going to end up having, that's the type of problem that you're going to see. But like I said, you know, find the equivalent capacitance. Now I'm gonna here you go. Okay, the equivalent capacitance is gonna be C1 plus C2, right? Again, like I said, this is gonna be the simplest problem that you are gonna see out there of capacitors in parallel. You don't have to worry about getting the invert. Here you go, the inverse. Okay, one is 1 milli, the other is 0.47. You know what? 1 millifarad. Oops. 1 millifarad. The other one is 0.47 millifarad. 640. So we get 1.47. Okay, I'm not gonna write that down, but you got the idea, right? Then you have other types of problems too. You can have two capacitors in series, right? Here you go. Let's get the two capacitors in series here. Okay, here you go. I'll copy this one. Two capacitors in series. Find the equivalent capacitance. That's the second easiest problem that you're gonna find. Here you go. In this case, it's gonna be capacitors in series. Same thing, right? So let's go back here to the, I'm gonna do the calculation right now. Capacitors in series. Okay, go. C1 is equal to 1 millifarad. C2 is 0.4 millifarad. 47 millifarad. Two capacitors only. Then you do the math, right? Here you go. I'm gonna go to Excel, do the math. You want to do the math in Excel. 645, we're getting there. Okay. Okay, so it's gonna be 1 divided by 1 plus 1 divided by 4.47. That's the equivalent, that's gonna be 1 divided by the equivalent capacitance. Okay? Let's see here. Subscript. Yeah. And then if you want to get the equivalent capacitance, what you have to do? You have to get the inverse. You have to get the inverse of this value here. And I'm getting 0.31. Let's not forget to put the units, right? Here you go. It's gonna be C1 here, C2 here. C1, C2 is gonna be Faraday, right? Farad. Farad. Oh, I forgot to put 10 to minus 3 here, huh? Let's put 10 to minus 3 here because it's millifarad. Here too. 0.46 times 10 to minus 3, right? I forgot to do that. And let's see if I got it right. Yeah, okay. The C1 was 10 to minus 3. Oops. Don't forget to put equal. Let's look at the numbers, right? The other one was 0.47 times 10 to minus 3. Okay, so let's put everything in scientific format. Format, number, here you go. Scientific, so you can see better the results. Which one is less than what? Okay, so here you go. We have 1 millifarad here. We have 0.47 millifarad here. And look what we get for the equivalent capacitance. The equivalent capacitance ends up being less than this guy. See that? It always happens like that when you connect the capacitors in parallel. Okay? I'm going to put here capacitors in parallel. Always happen like that. If they are all connected in parallel, capacitors in parallel, the equivalent capacitance is going to be less than the smallest value that you have here. Now, if you have the same two capacitors connected in series, that's easier, right? Because it just requires a sum. The C equivalent, the equivalent of the capacitance is going to be, one plus the other. This plus this one. The capacitance ends up to always being larger than the largest of the capacitors. You can do that for 2, for 3, for 4, for 5, and we can prove that mathematically without resorting to numbers, just by resorting to algebra. Okay? So 6:50 right now. We can stop now and let's have our break. Let's have our lab. Okay? I see you upstairs.